Hi, hello, welcome. This is Jayalakshmi of IG College of Engineering. As we are continuing that third video in that first unit is ground reflection model. Let us start with that one. What is that ground reflection model? It is also called as two-ray model. When you see this diagram there itself, it is known to you. In the free space model, we have considered only the line of sight path only, but when you are going for long distance and that reflection waves also cause effect in that received signal strength. So this was found reasonably accurate for predicting large scale signal strength over distances of several kilometers for mobile radio system using tall towers. It is good for system that uses tall towers over 50 meters tall. It is good for line of sight microcell system in urban environments. The total E total is the electric field that results from the combination of the direct line of sight path and a ground reflected path. The maximum transmitter and receiver separation distance is the only few tens of kilometers, and the earth may be assumed to be flat. So at that time the total E total, the total electric field, received electric field is given by that the direct line of sight component electric field plus the ground reflected electric field component. When you are going for the two-ray model, referring to figure, HT is the height of the transmitter and HR is the height of the receiver. If EOI is the free space electric field in volt per meter and at a reference distance D0 from the transmitter, then for D is greater than D0, the free space propagating electric field is given by E of D comma T, that is equal to E0 D0 divided by D into cos of omega C into T minus D by C, where E of D comma T, the modulus E of D comma T equal to E0 D0 by D represents the envelope of the electric field of the at a D meters from the transmitter. Two propagating waves arrive at the receiver, the direct wave that travels a distance D dash and the reflected wave that travels at a distance D double dash. The electric field due to the line of sight component at the receiver can be expressed as E line of sight can be given as E D dash comma T, which is equal to E0 D0 divided by D dash cos omega C T minus D dash by C. Similarly, that E dash due to that and the electric field for the ground reflected wave which has propagation distance D double dash can be expressed as E dash equal to 1 plus L into E dash, and this according to the laws of reflection the dielectrics theta I will be equal to theta naught. That ground reflected wave EG is given by D double dash comma T, which is equal to R into E naught D naught divided by D double dash cos of omega C into T minus D double dash by C. Okay, for small values of the incident and reflected wave, theta I will be equal to theta naught, and that resultant electric field, the reflected wave is equal in magnitude and 180 degree out of phase with the incident wave. So the resultant electric field, assuming perfect ground reflection, is the vector sum of E line of sight and the EG, and the total field will be given by the addition of these two, that is EG equal to line of sight plus E dash. Then we have discussed that one, that diffraction, reflection and refraction causes the problem in that unique problem we are facing when you are going for that line of sight. So diffraction occurs when radio path between the sender and the receiver is obstructed by an impenetrable body and by a surface with sharp irregularities. The received field strength decreases rapidly as the receiver moves deeper into the obstructed region. The diffraction field still exists and often has sufficient strength to produce a useful signal. The diffraction explains how radio signals can travel urban and rural environments without a line of sight path. See that one in diagram, it is given there. When there is an obstacles, the line of sight path has to be penetrated through that building, that is obstacles, or else it will be diffracted path is given by that other path. The phenomenon of diffraction can be explained by Heightens Principle, which states that all points on a wave front can be considered as a point source for the production of secondary wavelets, and that these wavelets combine to produce a new wave front in the direction of the propagation. The field strength of the diffracted wave in the shadowed region is the vector sum of the electric field components of all secondary wavelets in the space around the obstacles. So when you are transmitting that one, that line of sight path transmission as well as the wave front caused by the obstacle diffracted wave is summed up, and we will get the original signal. Then scattering. When we are discussing about that scattering, the medium which the wave travels consists of objects with dimensions smaller than the wavelength and where the number of obstacles per unit volume is large or rough surface, small objects, foliage, street signs, lampposts. Then we will have that scattering problem. See that one where we are having that scattering. Even a plant we are keeping in our house also causes the scattering. Scattering generally difficult to model because the environmental conditions that cause it are so complex. So modeling position of every street sign is not feasible. Then we are going for the next topic, that is parameters of mobile multipath channel. Power delay profiles are found by averaging instantaneous. First one is power delay profile. In that one we are going to discuss about time dispersion parameters. For calculating this time dispersion parameters, we are in need of power delay profiles that are found by averaging instantaneous power delay profile measurements over a local area in order to determine an average small scale power delay profile. Time dispersion parameters. The time dispersive properties of wideband multipath channels are most commonly quantified by their mean excess delay and RMS delay spread. The mean excess delay is the first moment of the power delay profile and is defined as tau bar equal to sigma ak square into tk divided by sigma ak square, or it can be given by sigma p of tk into tk divided by sigma p of tk. The RMS delay spread is the square root of a second central moment of the power delay profile and is defined as sigma t equal to square root of tau square bar minus tau bar square, where tau bar square can be given as that already we have discussed sigma k ak square tk square divided by sigma k ak square. The typical values of RMS delay spread are on the order of the microsecond in outdoor mobile radio channels and on the order of nanoseconds in indoor radio channels. The maximum excess delay of the power delay profile is defined to be the time delay during which the multipath energy falls to x dB below the maximum. Next, coherence bandwidth. It is the measure of the range of frequency over which the channels can be considered flat. That is, channel passes all spectral components with equal gain and linear phase. It is a definition that depends on the RMS delay spread, and that coherence bandwidth BC can be given by 1 by 50 sigma, where sigma is the delay spread. Two sinusoids, the frequency separation greater than BC are affected quite differently by the channel. If we define that BC is the range of frequency over which the BC can be given by 1 by 5 sigma tau. If we define coherence bandwidth as the range of frequency over which the frequency correlation is above 0.5, then this is called as 50% coherence bandwidth. Next, we are going for the Doppler spread and the coherence time. Doppler spread and coherence time are the parameters which describe the time varying nature of the channel in small scale region. Measure of spectral broadening caused by motion Doppler spread BD. It is defined as the maximum Doppler shift FM, which is equal to V by lambda if the baseband signal bandwidth is much greater than the BD. Then effect of the Doppler spread is negligible at the receiver. If the BD is greater than the baseband signal bandwidth, then the effect of Doppler spread can be negligible. The coherence time is the time duration over which the channel impulse response is essentially invariant. If the symbol period of the baseband signal is greater than the coherence time, then the signal will distort, since the channel will change during the transmission of the signal. The Doppler spread and coherence time are inversely proportional to one another, that Tc is equal to 1 by Fm. If the coherence time is defined as the time over which the time correlation function is above 0.5, then the coherence time is approximately given by Tc equal to square root of 9 divided by 16 pi Fm square, that is 0.423 Fm. The definition of coherence time implies that two signals arriving with a time separation greater than Tc are affected differently by the channel. For example, for a vehicle traveling at 60 miles per hour using a 900 megahertz carrier, a conservative value of Tc can be shown that to be 2.22 milliseconds. Next, the types of fading. There are two types. Basically, there are two types of fading. One is large scale fading and small scale fading. We have started with that large scale fading. In that one, we have discussed with path loss models. Then shadowing. When you are going for that small scale fading, we are having multipath delay spread, Doppler spread. In the Doppler spread, we are having that fast fading and slow fading. In multipath delay spread, we are having flat fading and frequency selective fading. Fading, the time variation of received signal power due to changes in the transmission medium or paths is known as fading. The fading depends on various factors as mentioned above. In a fixed scenario, fading depends on the atmospheric conditions such as rainfall, lightning, etc. In mobile scenario, fading depends on obstacles over the path which are varying with respect to time. These obstacles create complex transmission effects to the transmitted signals. Considering various signal related impairments and position of the transmitter and receiver, following are the types of fading in wireless communication. What is large scale fading? Another one is small scale fading. The small scale fading is further divided as multipath delay spread and Doppler spread. The Doppler spread is further divided as a flat fading and Doppler fading. Okay, the fast fading and slow fading. Large scale fading, we are having path loss model. We have already discussed that one. Then we are having that one, shadowing effect. It is observed in wireless communication. Shadowing is deviation of received power of electromagnetic signal from the average value. It is result of obstacles over the path between the transmitter and the receiver. It depends upon the geographical position as well as radio frequency of electromagnetic waves. When you are going for the small scale fading, we are having flat fading. The wireless channel is said to be flat fading if it has constant gain and linear phase response over a bandwidth which is greater than the bandwidth of the transmitted signal. In this type of fading, all the frequency components of the received signal fluctuate in the same proportion simultaneously. It is also known as non-selective fading. That is, signal bandwidth is lesser than the channel bandwidth. We will have this one. Similarly, symbol period is greater than the delay spread. We will have this one. The effect of flat fading is seen as decrease in the SNR. These flat fading channels are known as amplitude varying channels or narrowband channels. Next, frequency selective fading. It affects different spectral components of a radio signal with a different amplitude, hence the name selective fading. Signal bandwidth is greater than the channel bandwidth or symbol period is less than the delay spread. We will have that one, frequency selective band. Based on the Doppler spread, there are two types of fading, that is fast fading and slow fading. This Doppler spread fading types depends on mobile speed, that is speed of the receiver with respect to the transmitter. Fast fading, the phenomenon of fast fading is represented by rapid fluctuation of signal over small areas. When the signal arrives from all direction in the plane, fast fading will be observed for all direction of motion. Fast fading occurs when channel impulse response changes very rapidly within the symbol duration. If the symbol period is greater than the coherence time or signal variation is less than channel variation, we will have that small fading. Then we are going for that slow fading. Slow fading is the result of shadowing by buildings, hills, mountains and other objects over the path. a low Doppler spread. Due to that, when signal period is lesser than the coherence time, or signal variation is greater than channel variation, we will have that slow fading. Slow fading results in loss of SNR. Error correction, coding and receiver diversity techniques are used to overcome this effects of slow fading. With that, we have completed all the topics in that first unit. If you are having doubt, free sending the questions.